Good morning, ladies and gentlemen, to the next episode of our web seminar Wednesday in Composites United. My name is Thomas Heber from Composites United, and I'm happy to present you our guest today. Today we are talking about, it's all about advancing bio-based polymers, especially as the topic is sustainable solutions for composite applications. And our guest is Christopher Gardel from Schill+Seilacher Struktol GmbH. Nice to have you here, Christopher. You are technical sales manager, and I'm right, at Schill+Seilacher.
And
Otherwise, you can
project
correct
manager
me.
and some few other things, yes.
Yeah, you do the stuff that is necessary in the company. Okay. The stage is yours, Christopher. Yeah, we are curious about your presentation.
Yeah, thank you. Thank you very much. Um, a very warm welcome from my side to our web seminar Wednesday. I will give you today a little bit an inside view of, firstly, who is Struktol, because I'm pretty sure a lot of you doesn't know us. And then I will go into our current development in bio-based polymers. And I will answer the question which I mentioned before with the announcement, is it bio? Can you eat it? But I will come to that at the end. So yeah, Christopher Gardel from Struktur Schill+Seilacher. We are based in Hamburg, and I will show you shortly a little bit of our company. Um, we are dating back to 1877, started with preparing leather. So this is where the company is coming from. Um, we are still today making some additives for leather producing. So this stayed till today. But we evolved into a company really which does chemics all over the place. For example, our department, the reactive polymers. Um, we are mainly located in Germany, so in Hamburg, in Böbling, where the company started in 1877. And we do have one site in Pirna. We have two sites in America to cover up the American market a little bit. And we just started a little outside company in Malaysia. Mostly for the colleagues of the rubber department, because we are doing quite a lot of things for rubber and therefore for tires. And most of the tires are produced in Malaysia. Um, Here you can see which of our departments are producing what. And as you can see, we are the only ones located in Hamburg. So we have our R&D in Hamburg, we have our production in Hamburg, so everything is coming out of Hamburg from our side. And in the future, we could maybe go also to the others to cover up some other markets. Um, a little bit of interesting thing about us, we do have quite a lot of people in R&D. So we have 12% directly in R&D located, and also 12% in application lab, which is also basically R&D work. So that we have quite a lot of R&D for us to come up with new stuff. We are using that also. We, as the reactive polymers, have one of the biggest R&D offices, and so this is where the ideas is coming from. A few facts about Hamburg. So 270 employees in Hamburg, and we're doing 42,000 tons a year, and only 3,000 around are coming from our department. And from that 3,000, 90% is toughening. So the reactive polymer business is still quite a side business. And we are now trying to grow that with our bio-based polymers. If you look at the whole group, we are at around 1,000 people and producing 144,000 tons. So We are quite a big player, I would say, in the chemists industry, and but not known for what we are talking about today. Um, Now coming a little bit in the direction where I'm going to talk about sustainability. So we have a clear path in the company for sustainability, like a lot of companies now do. And we in our department are one of the leaders when it's coming to sustainable bio-based materials. And yeah, I'm going to show you a little bit of the insights where we are at the moment. So we have three departments in Hamburg. Uh, I mentioned it. The rubber department is the biggest one for us. So you can, in every good tire you buy is something from us. We also do have antifoam, silicones, latex additives, release agents. Sadly, the release agent guys doesn't have release agents for composites. We are always looking into that, having discussions. Maybe in the future there's coming something. And I'm coming from the reactive polymers and flame retardants. And yeah, I will show you now a little bit of what do we have in our department. One of the biggest advantages we have is we can go from the lab to the production in one facility. So our development is quite near at the production. So we can go from 2.5 kilos from the lab over 25 kilograms in our technical department to 500 kilograms and then going into the production reactor. And one of the USPs we have in Hamburg is we can handle things we say are viscous. You would say it's solid. So 30 Pascal seconds at 120 degrees is, if it's not 120 degrees, basically a solid. And we are able to work with these kinds of materials. So we do have four product groups in the reactive polymers: Polydis, Polycarbid, Polyvertic, and Polyflux. The first two are our toughening business for structural adhesives. So also in every car you drive is something for toughening in the structural adhesive from the big players. So we are delivering our toughness to the big players of adhesives. And the polyvertic are the reactive polymers, and polyflux is our flame retardancy range. Uh, yeah, with these products, we are going into the, as I said, the adhesives. We do deliver quite a lot of flame retardancy to prepreg producers. So a lot of fire retardant prepregs has our polyflux in it. We do castings, we go into composites more and more, and flame retardancy as for where you can use our additives, for example, in composites or other stuff. And the markets are the classic ones. Automobile is one of the biggest. We do have some things which are go into aviation, for example, the prepregs with the flame retardancies, railway transportation. You know the markets. So now coming a little bit more into our products we have at the moment. So this is our composite synergy matrix. What I tried to do with this one is normally you can get a system, so the combination of a resin and a hardener. What we try to do is we open up our portfolio basically and just say, okay, we have this range of resins and we have this range of hardness. And you can basically combine everything with a few specialities where the things really are put together. And so the aim is here that you just have to buy one base resin and can scope every of your application just by using different hardness. So you can have a little less of logistics, you have less storage, you are more flexible if you would like to use something else, would like to change something in the process. So this is the aim with our synergy matrix. And it would get even bigger because we then can even mix some of our hardness, for example, to change a little the pot life or other things. And the bottom, you see the range of our bio-based polyesters. These are already things which are on the market we are selling. Some of you may know them. These are 100% bio-based. I will come to that later and show you a little bit of, okay, where is the bio-based coming from and how are we producing the material. But so where are the bio-based epoxies? And basically, this will come up with a new column. We are developing at the moment a wide range of bio-based epoxies, which we are going to call the 3480X series. Yeah, so now I'll go into the bio. But first of all, what do you understand of a bio? This is one of the main key questions I'm always asking when I'm in a discussion with a customer, because there are different expectations on the term of bio. So, yeah, what is the term bio-based really meaning for us at the moment? A lot of people are thinking on bio, it's recyclable. This could be true. So a product which is recyclable could be named bio. So this is the first assumption. Um, the second one would be, okay, it's bio, so it's biodegradable. So I can just throw it in the wood and the animals will like it. But uh, you can do that, but this is also not what we are working on at the moment. And the third one is what we are doing basically is, okay, it's bio because of the bio-based raw materials. So our materials we're using at the moment are on from a natural grown source, and this is where our bio content is coming from. And yeah, the customer always wants all three together, which is sadly, I would say, impossible at the moment. But maybe we will get to that point in the future somewhat. So um, now we have bio-based polymers, or we're starting to develop these, but we still have a little bit of some problems. So as always, new things are more pricier than the old ones. So the prices for the bio-based raw materials are still higher than petrol-based. Um, It also can be that the availability is still limited compared to what we are used to on the petrol-based side. Um, we are still lucky because the demand isn't that high as the raw materials, so we are on the good side now. But as soon really this stuff is going to get into the market, the availability will be a problem. Um, One of the key things I'm going into will be the performance. So increasing bio content is always coming with a little bit of lack in performance. And I show you where we find the sweet spot to generate a high bio content with usable performance. And yeah, basically in the end of it all, you still have to scale it to some point. So now gave you a little bit of overview what it is, but yeah, and we do have a lot of problems. But who is going to use it? This is the main question. But at the end, we are all going to use it because we have to. We have to change a little bit our expectations. The demand from the market is growing. We do know that yeah, cities and others are demanding more and more bio content when things are going to be changed. So the markets will be coming and growing. And I will show you now one example where we are coming from. So we are working in an open-funded project called the Shoreliner. And this is based on an example with a problem, the MDA1. The MDA1 will be a turboprop two-engined yeah, electric flying airplane, which is developed by M&D Aircraft. And we are developing parallel the bio-based resin for that airplane, which was the base for everything we are looking now into. Um, it's planned to be finished at around 2030. So the demonstrator should be flying around 2028, hopefully. And the key advantage of us is so we are developing the resin, the bio-based resin, parallel to the airplane, which then will lead to a flight-approved resin in the future, the first bio-based flight-approved system. And this is where we're aiming at the moment. So why is M&D doing this kind of airplane? So there is an increasing demand of regional air mobility, so short distances with an airplane, just to come up with the growing speed of the economy. And nobody of us wants to fly with these old turboprop petrol-based planes anymore. Um, the second thing is that these kind of airplanes are basically dying out because there is not that much of companies who are producing these kind of airplanes anymore. And as I already mentioned, there is already the drive for a carbon neutrality. Um, so based on regulations, we have to go electric flying. We have to have bio-based materials, and this is where we are going at the moment. Um, So the vision is the reimagined zero emission aircraft, and they will deliver a certified clean sheet design electric aircraft. So the advantage from this aircraft basically um, is that it's a classic aircraft and it's not thought new like a volocopter or whatever there is on the market. So everything you can see is a classic airplane design. I will come to that in a little bit. Um, so the solution with this airplane is basically, okay, we will unlock the regional air mobility with electric flying. Um, it will be highly efficient with lower operating costs. And you will have opportunities over the long haul because we will have to go electric also in flying. So the airplane is itself, as I said, is a classic design. So it's not a new thing they want to develop. Everything which is high voltage energy will be placed in the engine nacelles. So the power grid is basically separated from the main hull of the flying airplane, which is a great benefit. And it's also an opportunity to just change the energy source you put into the cell. So there are thoughts of, okay, it's fully electric with batteries and the motor in the cell. You can go hybrid. So there are turbines which generate electricity for the batteries and the electric motor based on hydrogen. You can put a classic petrol-based engine in it. So there is a lot of variety in that airplane. And also, it will becoming basically a family. So at the moment, there are 9 people who will fit in that first airplane, and they want to grow till 30 or more. So yeah, this is the first example of where the bio-based material is going. But now it's the question, okay, where is the bio coming from? So in our case, for the epoxy range, our bio or the raw material for our epoxies is cashew nutshell liquid. So you have the cashew nut, and between the nutshell and the kernel, there is a liquid which is called CNSL, and this liquid is quite interesting. Um, it is inedible, so we will not use it. So when we want to eat the cashew nut, we will have leftover. It's very good available. It's cost effective because it's basically trash at the moment till we use it. and you can do quite good chemistry with the basics of that liquid. So how to come from that liquid to something which is going into epoxies? So the liquid contains four main parts: cardol, anise, anarcardic acid, 2-methyl-cardol, and cardinol. And the main thing we want to have is the cardinol. So how do we get the cardinol? So basically, the first route is just by distilling the liquid and the cardinol is left. And the second route is using the anarcardic acid by decarboxylation and also coming to the cardinal. And this cardinal is interesting because you can then go on the OH group and just put something epoxy-like on it. So you do an epoxidation. And this is then the base material where every raw material used at the moment is coming from. So for the hardness, for the resin itself, and so on. And from that on, we are going to formulate. So we try to formulate the future and from the raw material to a usable product. As I said, it's now we do have a bio-based raw material range, and we want to get as high as possible in the bio-based range. But we want to keep the properties as close to the petroleum-based ones as possible. But the problem is we have a decreasing in the properties by increasing of the bio content. So what we do at the moment is, yeah, we start with initial formulations by our internal know-how, and we do have now a really, really good baseline. And what we now trying to do is use machine learning, basically. So we are going to feed machine learning, which we're doing now in parallel, to optimize really the last percentages with bio content and performance. What we did and what will I show you now is the correlation. And we started with a base, and the base was available system which could be go into an airplane, and the baseline was an Hexion LR285. This is a flight-proof resin, which good mechanical properties. So these are the ones we all use still at the moment. It's not exceptional high, it's not low. This is good. So we use that. This is the baseline. Okay, and where are we standing now? We do have quite a lot of formulations made, and these are not all. This is just an overview. And maybe you can now see the things I mentioned in the beginning. So we do have to the right an increasing amount of bio content in the formulations. And you can clearly see that there is a decreasing in the performance. And this is the problem we have at the moment. But not as big as it seems at the moment, because yeah, it is decreasing. But the question is, how much do we need from what? At the moment, we have one formulation which is the one which is going to be the flight, basically the flight approved material, where we on point fit every performance we needed to have. It has the same TG at around 120 degrees. It has the same mechanical properties, and we are over 30% in bio content with this system. But we can go up to 50% at the moment, but then lacking in performance, which are not suitable for flying. But the question is, do we really need that high of performance in other applications? So we can go higher with the bio content by lacking in performance, but how much performance is really need in which application and for which product? And what we can now do at the moment is finding the sweet spot. So we can find the maximum bio content to the performance you need to have, basically. And this is where we are going from this. But a lot of you say, okay, 50% is nice. But where do we go from there? Uh, we can go to 100, basically. We already have. But we have to change the material. So we are now going from an epoxy-based resin to um, a polyester-based resin. Because here we have a little bit different of raw material background, and we can play a little bit more. So how we put together the 100% of bio-based resin. So it's a unsaturated polyester resin, what we are doing at the end. It's chemically identical with what you are used to, basically identical. So we're coming from really natural growing raw materials, which is industrial corn and sugar beet or molasses made of sugar beet. And to be clear, these are products which are used to be industrial. So this is not used to be edible. And the industrial corn, the raw material is coming not directly from the corn, it's coming from what it's left over by generating methane for generators. So the leftover is then again fermented, and this is the base for what is coming out of it. So these are the two bio-based raw materials. As I said, these were then processed by fermentation, so a natural process, with yeah, basically bacteria. Um, and from these fermentation materials, we go into a bio-based diol. This is the first part of the polyester, and a bio-based carboxylic acid. Then what we are doing is we do the esterification reaction. And from that reaction is coming out the Polyvertec 3830 series. So the first material we had was the 3830, which is 100% bio-based. Or to be exact, it's 99.9% when we really look into it, because there are just a few tiny bits of processable additives we have to use, which are at the moment not bio-based. So the 3830 is a classic polyester system with a very high viscosity. And we dilute this system. Normally you use styrene, so this is the smell you're used to when you're working with polyester resins. And we are using a styrene-free alternative. So we can adjust the viscosity between 200 and 5,000 millipascal. So the normal range you would have used in all of the composite processes, you know. And what you can also do is SMC. So the classical big markets based on polyester resins are usable for this material. And we do have quite good or really, really good products out of pultrusion, for example. We do have a customer who is now really going to mass production in pultrusion with the finest surface I ever saw from pultrusion. So this is really cool. So, and there's the question we waited for. So it's based on corn and sugar. So can I eat it? No, I have to disappoint you there. It's as I said, chemically, it's just the same as the petrol-based one. It's just the raw materials. But so we cannot eat it. But where is the advantage? We are helping to make the industry a little bit greener. So what we can achieve at the moment is we are reducing the CO2 impacts of the materials. So, for example, a classic UPR is starting at around 3.8 CO2 per kilogram, and a classic epoxy is at around 6.6 kilograms. So UPR is in base a little bit better. And what we can achieve at the moment is, on paper, I would say, 25% reduction for our UPR. So our bay-based Polyvertec 3830 has at around 2.8 kilograms of CO2. The problem is the same for the epoxy base. So these are at around half of the original ones. The main problem is we are lacking informations from the raw materials. So The informations we now have at the moment are basically the yeah, source for these. But just for an example, we do have raw materials on the epoxy side, which start with minus 17 kilograms of CO2, just by if you add in the growing of the material. So you have a big minus in the start. And this is the problem I have with the poly 3830 at the moment. The raw material producers are still not able to provide us the right LCIA numbers, which in my opinion will start with a minus. So the material should be a lot better. Um, in my estimation, the material will be landing under a kilogram per kilogram. Yeah, this is the aim. And I hope I can present you a little bit of more informations in the future for the LCA nodes. Where are we going from here? Just a little bit of a view in the future. So at the moment, as I said, we are at a 50% for the bio-based epoxies. What we're now doing is we're widening the range with our additives so that we are going into uh, bio-based resins with flame retardancy, with toughening. So we can go into the adhesives and so on. So we are starting to use the bio-based raw materials, for example, for our additives, so that we will get bio-based additives. And I also mentioned that we started to do machine learning for further optimization of these products. And this will take quite a time because every iteration you have to produce the material, test it, put the information back into the machine learning, then run the machine learning again, doing them again. And I hope till the end of the year we will have some first results of the machine learning. And hopefully we can really increase the performance over this a little bit. Yeah, basically, I'm coming to an end. And I have to thank a lot my R&D department at PC3 and at Struktol and the partners we are working with at the moment. And I totally have to thank das Bundesministerium für Wirtschaft und Energie because this is based on a funded project. And yeah, M&D Aircraft for the information to the airplane. And so thank you very much for your attention. I will now try to answer your questions. Please consider I'm just an engineer. If it's chemical, I have to forward it to my colleagues. But I will try to give you an answer as soon as possible. Yeah, and I'm looking for your questions.
Thank you very much, Christopher Gardel, for this great presentation. I'm also just an engineer, but I could follow you.
That's great.
It was great. And yeah, we wish you good luck and many success on your way further in this direction with Schill+Seilacher Struktol Group.